Hi, my name is Ramsey Zeitoun. I work for Twist in the R&D group. I've been working on this project pretty much since the inception of the project. With target enrichment and with DNA sequencing, we're looking to capture as much information as we can. We could do that with whole genome sequencing. All of our information is present, but you may never be able to identify it simply because there's so much other stuff around. So with target enrichment, we can select for our sequences of interest, but the problem is you can introduce bias. If your probes aren't 100% efficient or have the same efficiency, you'll capture fewer, you'll lose target information, first off. Second off, you can introduce non-uniformity and biases, which can ultimately limit the capture efficiency of your process and what you can learn from your process. So I just drew two colored baits right there, two colored probes right there. You can see you can potentially have a non-uniformity, which would require more sequencing to identify the same amount of molecules with the same coverage. My favorite example of the implications of this come from this paper right here in 2014, where they compared the heterozygous SNP calling sensitivity between whole genome sequencing and whole exome sequencing. Basically what they found is that you need about 14 to 18x coverage, on-target coverage, to cover about 95% SNP sensitivity for whole genome sequencing. With whole exome sequencing, the kits and the non-uniformity out there makes it so you need 39 to 40x on-target coverage just to get the same sensitivity. So when we approached this, we said, well, perhaps we can engineer our probes better to improve the uniformity of capture to kind of close this gap between the whole genome sequencing and whole exome sequencing, ultimately reducing the amount of sequencing needed to get the same amount of information. So that was really our goal, is how do we engineer baits and probes to be more efficient and universally more efficient? And how do we do this in a reproducible and understandable way? We took an approach that's used ubiquitously through engineering, which is a design, build, test, learn cycle. Basically, we can design probes, we can test out dozens of hypotheses at once, build the probes, test their performance just using NGS sequencing, learn from the designs, learn from things like the thermophysical properties, the mapping of different probes across different genomes, and learn how they actually interact to predict an efficient performance. Now, one thing you'll notice is this is an iterative process where we can keep cycling through this to try and learn more information and ultimately learn how to build a better system. But with an iterative process, the more cycles that you need to go through this, the more you can learn. So ultimately, any step slowing you down is going to be the rate-limiting step to learning how to engineer a better system. And when we approached this, our first problem was, how do we actually build probes? Fortunately, I'm at Twist, and we have a great system for building oligos and making them into probes. The nice thing, it's a silicon-based system, which gives us independent control of our oligos. So that's great for two reasons. One, we can design oligos and systems and panels of varying size and complexity. We can look at just a few genes with a handful of oligos, or we can look at an exome size or greater. And then, number two, we can define the composition of the population to really tune the complexity of our capture population that will enable us to actually design and engineer a great system that can capture uniformly. Now, we figured out how to scale this from the 1 femtomole per oligo that we write to 1 picomole per probe or greater that we need for target enrichment. And Emily gave you a little bit of a preview, I guess, or a little clarity on how we do that and how we developed a process for manufacturing probes in a reproducible and controlled way. So I'm not going to go too far into that, but basically we make double-stranded probes and we don't introduce bias into the process. So now we have a great build process. It takes us about 3 weeks to go from sending the design to having probes ready for action. And now we can iterate through this process to try to learn. Before I start showing some of the results of our learning, I'm just going to show this graph, which is essentially a histogram representing coverage uniformity. Right here is the coverage versus the percent of target bases having that coverage. And I put two curves here. One is a twist green curve, which represents highly uniform capture, where most of the bases, target bases, are represented within the same capture, or within the same coverage, having the same coverage amount. Whereas this other curve I drew is a larger one, where it's more diffuse with the coverage among the target bases, meaning that you would need to cover and sequence more to get the same coverage in your population. That's not good. That's not what we want. So we start to apply this design, build, test, learn strategy. Here's just 2 revisions of the process, 2 iterations. The first one is right here in this gray curve. We get pretty good uniformity, but it's a little larger than we want. And then we do the next iteration on the process, and we get a tighter curve. More bases have the same % target coverage. And we can keep doing this process, keep learning how to best design the system, find where our weaknesses are, address them, and eventually build a model. Model takes into account thermodynamics, the genome, our panel complexity, as well as the process itself. So we can take our targets, build a design panel, and then we have our manufacturing process, which is really good, and then eventually get probes that are functional and efficient and engineered. This is the heterozygous SNP sensitivity calling. So we built an exome. This is the exome we're currently selling. So how does it, can it close this gap or narrow this gap, should I say? And it did that very well. So this is 95% sensitivity for NA12878. With whole genome sequencing, which we ran ourselves, took about 56 gigabases of sequencing, 15x coverage to call 95% heterozygous SNP sensitivity. With whole exome sequencing, we got about 16.5x coverage for 95% sensitivity. That was 1.3 gigabases. And this wasn't at the compromise of other metrics. We still had 15% off target. We had a huge number of molecules captured because remember, I'm saying we were engineering all of our probes to be efficient. So we had 3% duplication at 50x, and our fold 80 or uniformity was 1.35. I'll explain what fold 80 means in a second, but uniformity, I want you to remember that number. That's about equal to, it's a little bit worse than whole genome sequencing in terms of capture efficiency and narrowing the gap between the two. So fold 80, uniformity, basically tells us the amount of sequencing we need to cover 80% of our bases. So suppose there's a mean coverage of 30x, and 80% of our bases are covered at 20x, then our fold 80 is 1.5. Higher fold 80s are worse, lower fold 80s are better, and here's the 2 curves calculated for the fold 80, just to give you an idea. Here's a few other panels we designed with our own process. It's another version of exome, another flavor we made, and a small panel, pan-cancer panel, 806 kb, and it was even more uniform than our exome panel, which is good. Another question is this reproducible? So we can show that really easily. We performed 2 8-plex captures. I'm only showing 2 sets of samples right here. And we compared the capture efficiency between probes within a capture and between 2 captures. When we compare that, each dot represents the amount of base calls per probe, and we see there's a high correlation. Not only that, we see that between intra-capture and inter-capture reproducibility, we see about the same correlation. The reason for that is probably because most of our noise is just due to technical artifacts like sampling error, the fact that we don't sample infinitely. And we would expect this efficient capture, mainly because, or reproducible capture, mainly because all our baits are acting efficiently. And they're probably less sensitive to technical variation between processes because they're very efficient and there's a while to fall before they start reducing their performance. So another question that we had is, can we actually use this design, build, test, learn process to try to figure out how to engineer probes to capture more specific coverage? And so, for instance, you can have non-specificity from pseudogenes, from simple repeats, from low complexity regions. And so we can target these, we can design probes to target only the region we want, not the region we don't. So this is that 806 kb panel. Initially, we had about 21% off target. We were targeting some kind of nasty stuff. And so we did a few iterations, learned how to, or one iteration here, learned how to design better probes, and eventually reduced that about 60, that off target 64% to 7.6% off target from 21%. And consequently, and part of the process, we were able to reduce our fold 80 from 1.29 to 1.24. And just remember how that fits into that curve I showed you earlier about whole genome sequencing versus whole exome sequencing. So finally, I gave you kind of an idea of how we have good control and a good understanding of how to design probes to give you an efficient and reproducible capture. So the next question is, how can we modify our current system? Can we use what we know to develop probes that will work and play nicely with what we make, like our exome? So we made a spiking panel. It's about 120 kb from our, and we can add that to our 33.1 megabase exome. We can do it in different flavors, customize it. So our exome We don't have any spike in. We can do 1-to-1 exome to spike in just to look at how our coverage can be affected. Or we can do 2-to-1, for instance, if we're looking for somatic mutations or something where you need a little bit higher coverage or a little bit more confidence in your sequencing. We can do that as well, or really any flavor that we want. So here's a histogram of our exome spike in, 0-to-1. So our exome, of course, looks nice, very clean histogram data. About 2.8 gigabases of sequencing. For our spike in targets, we get about 1.5 mean coverage. 2% of our targets are above 20x. Reason for that is just because some of the targets would be included in the shadow of our capture. With 1-to-1, we are able to successfully and uniformly cover our targets of interest in the spike in. About 34.9 mean coverage. 91% of our targets are covered greater than 20x. That's, again, 2.8 gigabases of sequencing. And 2x spike into exome, we're able to get a twofold enrichment of our spike in targets. 97% of our targets are covered within 20x. So it's great. It gives you the, by being able to predict how to design baits and probes and systems, really, we can predict how to really engineer something to be customized and flexible towards whatever we want to learn and look at in a uniform and reproducible way. That's really the approach we're taking. We're doing this design, build, test, learn. And we've learned a lot on how to engineer target enrichment systems, and we've been applying it to many different products. Here are some products that we've made. We've made, obviously, an exome and a custom exome. And that takes into account the fact that we capture so uniformly. It's probably a good way to, a good direction to do your exomes with Twist. We've made cfDNA panels for people. Since all of our probes capture very efficiently, we capture so many molecules that it's beneficial for cfDNA, ctDNA, to be able to use our probes to capture. Done some we've made panels for viral sample genotyping, which I think we'll hear about soon. Pretty excited for that talk. As well as other applications such as cancer and epigenetics methylation. That's basically our process. It's something where we can learn. We have a really great system. I'm hoping that, potentially with this control of being able to design probes, we can do more in the future and perhaps open up new directions of inquiry that we haven't been able to yet because of the predictabilities of systems. Thanks.